Hello, and welcome to physics video Optics.7, Dispersion and single slit diffraction. In this video, we will look at what is happening when light reaches a barrier and either goes through it or goes around it. Wavelengths of visible light go from about 400 nanometers to 750 nanometers. The shorter the wavelengths are ultraviolet, the UV over here, and the longer wavelengths are infrared on this side. I'm pretty sure that you've seen this spectrum before, but let's review it anyways. It's important to this portion of our optics studies because of the fact that the spectrum is a continuous spectrum, not only of colors, but also of wavelengths, and therefore also of frequencies. And remember from when we were talking about light changing and refracting as it goes into different media, that means that each of the different frequencies of white light will refract in different ways and therefore will bend in different ways as it goes through different medium. I oversimplified the index of refraction earlier when we first introduced it, but now we need to look at the fact that the index of refraction of a material varies somewhat with the wavelength of the light. This variation means that when light goes into a prism, for example, not all of the frequencies of light react the same way, and this is why a prism will split visible light into a rainbow of colors. So, for example, you can see if we shine violet light with a wavelength of 400 nanometers onto a piece of quartz, then quartz will act like its index of refraction is about 1.57 or 1.56 rather. But if we put orange light through quartz, then its index of refraction will be a little bit less than that. It's especially noticeable when you are looking at the silicate flint glass here, when violet has an index of refraction going through of about 1.66, whereas red at the opposite end of the spectrum is much closer to 1.61 or 1.62. Here you can see the result of this, where the white light comes in, hits one side of a prism, and then they all refract at different angles. And then when the different colors of light, which have now been split up, refract again at the other side of the prism, they produce a rainbow in the order of Roy G. Biv. The atmospheric rainbows are created by dispersion in tiny drops of water. Now, this is a new term that we've not talked about before. Dispersion, we've been talking about it as refraction instead. But when light is refracted, white light in particular, and it spreads out because of refraction, it is called dispersion. And now the dispersion is causing a different view for each observer of the rainbow, because each ray of white light coming into a rainbow that gets refracted and dispersed within the water drop comes back to the person's eye differently than it comes back to the next person's eye. Because notice that the bottom water droplet, the red misses the person's eye. Whereas for the top water droplet, it's the violet that misses the person's eye. This is why rainbows are individual. Light will also diffract around a single slit or obstacle. There was a great debate about what light was in the scientific world, whether it was a particle or a wave. Those that thought it was a particle were looking for evidence to support their claim in all of the experiments that were being done. And of course, those that felt that it was a wave were looking for evidence to support their claim. Oftentimes, though, the same experiment would come out with evidence for light behaving as both a particle or a wave. Or, as we found out later, the original conclusions that they had come up with turned out to be wrong because they just didn't have sophisticated enough equipment to make the measurements or perform the experiments well enough. The results of the experiments that went with the situation shown here, where you have a solid disk with light being dispersed and bent around the edges of it, seem to confirm that light was a particle, because this bright spot that appears in the center of the shadow was not present when the experiment was first performed. And later on, when it was performed with a better equipment where we could have all of the light coming in actually being exactly the same wavelength, then it was found that it actually supported that wave theory of light. So it's tough to say when we look back at the old experiments who was right and who was wrong, and we really have to take it in context with what the equipment they were using. But now we know that if you shine a light source onto a solid disk, then the waves that go around the edges of it will bend and refract and will form a shadow with a bright spot in the center. And the only way that that bright spot can be in the center is if there is wave behavior to the light, and it allows for constructive interference. It also led us to understanding how light behaves when it goes through a slit. Let's look at a simulation of light going through a slit and see how the slit affects the diffraction pattern that is produced. Okay, so if we take a look at this diffraction of light by a single slit and we vary things, we can see a nice picture going on here of the diffraction pattern. Now, right now, the wavelength of light that we're looking at is 600 nanometers, and the slit width is also 600 nanometers. So you can see at this point, there is just a continuous beam of light, line of light around on the surface, a screen here. Let's increase the slit width to 1200. So now the slit width is twice the wavelength of the light. And you'll notice that we're beginning to see a pattern. We still have the central maximum that goes from 0 out to about 30 degrees on each side. Then at 30 degrees, you have the first order minimums, and then the next maxima are significantly less bright than the first ones. If we continue this process and we increase our slit width more, we're now at a slit width which is 3 times the width of the slit is 1800 nanometers, and again, wavelength is still 600. You'll notice the same thing is occurring. The width of the central maxima is decreasing, and now we have 2 other maxima after that. So we have the central maxima, then maxima 1, and then maxima 2 on each side. Or you can look at it as saying we have the first minima and then the second minima. This first minima is at 19.5 degrees. Let's do it again. Now we're at 24. And again, the central maxima is still quite bright, but we have 3 other order maxima on each side. So we also have the corresponding 4 minima on each side. We can see if we move out to, say, the 30 degree mark, you can see that at 30 degrees we are at a minimum. Again, the K equals 2 minimum. The first maxima outside the central maxima occur at 21 degrees. So you can see if we make this width of the slit even larger, say 6 times the wavelength, we end up with getting a lot more maxima and minima. The initial minima is now only 9.8 degrees from the central max. The central maxima actually does get even brighter here. Let's turn on the intensity profile. And you can see that the central maxima is quite bright, and we have the arrows pointing where these 2 red dots are that are at the second minima. And you can see how quickly the intensity of the pattern decreases. Now, what happens if we change the wavelength? What if I make the wavelength decrease to, say, 480 nanometers? Again, now that the width of the slit is 3600 still, you get a lot more maxima and minima. And notice the same sort of intensity pattern going on there. If I decrease the wavelength even more, you can see that it's still doing essentially the same thing, where it is having lots more maxima and minima, but the outer lying maxima are so faint that we essentially can't see it.
So when we're talking about diffraction of light by a single slit, we can see that the relationship between the wavelength and the width of the slit is what's going to determine how many maxima and minima we see, and it's also going to determine how bright those maxima and minima are. Because now you can see my slit width is getting closer and closer to the wavelength, and the central maxima is decreasing in height but expanding in width as well.
In this picture, we can see a little bit better what was happening with the light on the simulation. If we focus on the graph on the end, we can see that there is in fact a relationship between the size of the slit and the position of the dark spots. The minima of the single slit diffraction pattern occurs when we have d sine theta is equal to m lambda, where m is which minima you are looking at, which number minima you're looking at, 1 central of 0 or the 1, the 2, or the 3. And it turns out that d sine theta equals m lambda works for all single slit diffraction patterns, and it will tell you where the minima of the slit is based on the wavelength of the light and the distance. So if we look at it from the slit perspective, we can see more clearly how the rays have different distances to travel before getting to the screen. If the light is coming in directly into the slit, so theta is 0, they all are going to have, they're going to be the same distance apart, and they're all going to get to the screen at the same time, so you will have a bright spot there. But if the light comes in at a slight angle theta, there will be a difference in distances that the wavefronts have to travel before getting to the screen, so that the top waves here, as shown, would have an extra lambda to travel, whereas the middle waves might have an extra half lambda, and the bottom waves would still have regular distance to travel. So at this point, you would end up with a dark spot. Then when the theta results in a wavelength difference of 3/2 lambda, it will again be bright. When the angle difference is going to result in a difference of 2 lambda, you will again have a dark spot. So you can see that it varies back and forth between bright, dark, bright, dark, bright, dark, where theta is 0, the wavelength difference is lambda, 3/2 lambda, or 2 lambda. All right, so let's do a quick example problem for a single slit situation. Light of wavelength 750 nanometers passes through a slit 1.0 times 10 to the negative 3 millimeters wide. How wide is the central maximum? A in degrees and B in centimeters on a screen that is 20 centimeters away. So we have a screen, we have a slit. This distance here we said is 20 centimeters. We said that the wavelength of light is 750 nanometers, and the slit distance is 1.0 times 10 to the negative 3 millimeters. So we have all of these numbers in different units, so we have to make sure we keep that in mind. The width of the central maximum goes from the first minimum on one side to the first minimum on the other side. So what we need to do is we need to use the equation that sine theta is equal to lambda over d to find the first minimum. So sine theta then is equal to 7.5 times 10 to the negative 7 over d, which is 1 times 10 to the negative 6, and these units come about by making them both into meters. So sine theta ends up to be 0.75, which means that the angle is 49 degrees. Now remember, this angle being 49 degrees is the angle from the center line out to the first minima. So really what we have here is that the total width of the angle of the maximum is 49 degrees at the top plus 49 degrees at the bottom, or 98 degrees is the width of the central maximum in degrees. Now the second part of this is asking us for what is the central maximum in centimeters. Looking at this picture here, we can see that in centimeters it's going to be equal to x plus x, or 2x is going to be the width that we're looking for. And we also know that we know this angle is 49. We know that the distance to the screen is 20 centimeters. So we could use tan theta is equal to opposite over adjacent. We know that our theta is 49. So x would be equal to 20 times tan of 49. We aren't interested in x though, we are interested in knowing what 2x is. So I'm going to just simply immediately put a 2 in there. So we have 2x is 2 times 20 times tan 49. And if we solve that, we find out that the distance that we are looking for, our 2x, is 46 centimeters. So our angle of central maximum we found by finding the angle to the first minimum. This is often called the first order. And then keeping in mind that we want the entire width, we had to not just go from the center, but we had to double that. And that got us the angle width, the angular width of the central maximum. And then we could use geometry to find out what the width was in centimeters. Quick intro to single slit diffraction and dispersion of light as it goes through prisms. And this is the sort of example that you're going to have to be able to solve in this assignment. Bye for now.